Good evening, everyone. Hope you're having a fantastic start to the week. My ears are too loud. Always. Yeah, welcome. So glad you could make the time to hang out with me and follow along while I do dumb stuff for a couple of hours. We should have some fun tonight. Still too loud. Who would have thought? There we go. Before we get started, I wanted to kind of take care of some housekeeping. First cab off the rank is femtoctf2021.clownshoes.party. I'll drop that in chat now if anyone wants to take note. If I remember on YouTube, it'll be down below somewhere. I came across this CTF on Mastodon this week. Raptor retweeted. I should have taken note of who the author is. But it's from Blackwing Intelligence. They're using it as a recruiting screen. But I just had a lot of fun. It was a really cool challenge. They asked me to kindly not stream it, otherwise it would have made it to the streams one day. But I think you should give it a go if you like fun challenges. Really important, clicking the GitHub link gives you the code. And the author said that all of this is in scope as a player. So there's nothing in this repository that you're not allowed to look at. You can make use of all of it. And what's interesting is if you go down the bottom, you get some useful references, including Cryptopals. And they tell you to use Ghidra, and you might want to know about smashing the stack for fun and profit. All of this sounds highly relevant to our interests, I think. And if you've been following the Cryptopals streams we've done so far, the attack that I ended up using to solve this CTF, we haven't explicitly covered it, but you should by now know enough to solve this type of challenge. Bit of a hint, go to Wikipedia and look at the diagrams of how various block cipher modes work and see if you can use what they give you to get something cool out of it. So just a really fun challenge. It does require a little bit of memory corruption, binary exploitation as well, but it's not too difficult. It's kind of on the gentler end of the memory corruption stuff. So do check out femtoctf2021.clownshoes.party. I thought it was brilliant. I've also, since the last stream, pushed all of the latest code up to GitHub. Frenchie, welcome, my friend. Took the time to rename all of these files, so now they're zero padded, so they sort nicely, so that was bugging me last stream. But I also made a few small refactors and tweaks to it, so I just wanted to run through a couple of those now, because some of them could be of interest to you. First thing was, at some point, I was raising a value error for basically saying what the hell happened here, as if to kind of say, hey Justin, your code has a bug, this conditional should never have been taken, and one of these should have always hit. I've basically, because value errors are meant to represent when the caller to a function gives a bit of a wonky value, which is not what's happening here. So I've swapped that out for an assertion, because that's what assertions are meant for. They're meant to gently surface bugs in the code rather than value errors, which are for yelling at the caller for calling you wrong. And conversely, I've got a habit, it's a bad habit. I always use assert as a shorthand for check that something holds, else complain. And I also use it for cases where, like in this case, callers to this function, the fixed XOR function, they're supposed to give two arguments, b1 and b2, of identical length. So as a shorthand, I always like to chuck in stuff like assert that the lengths are the same, if not complain. But this is where value errors are meant to be used. So I've switched that around, and I'll do my best to remember to use a value error instead of an assertion for yelling at the caller for calling you wrong. And I'll try to keep assertions for when the code has a bug that I want surfaced. And the reason why you want to use assertions to kind of surface those bugs and make them loud is because at the point that the assertion in the kind of the code correctness case is no longer holding, you're probably, as a function, about to return a wrong value and mislead the caller. So assertions are good for kind of failing loudly rather than failing silently and just returning bad data. And the last thing I did was tidied up one of my type hints for the callable in the Oracle work we were doing last stream. Turns out you can specify when you want this function to accept a function as an argument, you can specify what you want the signature of that function to be. In this case, I'm saying it has to accept bytes and return bytes. And that way, callers of this function will get yelled at in their IDE with a typing error if that doesn't hold. So, cool trick. I didn't realize you could actually be explicit about what the signature for a callable was. But I was having issues on stream last time when I wasn't getting those. I wasn't getting yelled at. I'm like, surely there's a better way to do this, and it turns out there is. So that covers off the refactoring that I did in private after last stream, just so that you're all up to date with where we are. And what are we doing? We're working through the Cryptopals challenges still. If you've missed the last couple of streams, they're up on YouTube. If you're watching from YouTube, hello to you. We're on set 2. So last stream we implemented PKCS7 padding. We implemented the CBC mode for AES-128 the hard way. You know, we're not actually just using a library to be like, do the CBC for us. We're kind of wrapping our ECB mode cipher implementation in a way that implements CBC, which was pretty cool. And then we built what we call a detection oracle for ECB or CBC. And this was fun. In this challenge, we basically created a class that has a callable function on it. And that function, 50% of the time it encrypts with ECB, 50% it encrypts with CBC, after kind of bookending the user-given plaintext with random noise. And we then had to write a function that would call that function with some input that would let the caller determine whether the callee was using ECB or CBC. That was kind of fun. And I think oracles are going to come up more and more throughout the rest of this series. And I didn't describe what an oracle was last stream. So as a really quick explanation for what I think it means, is an oracle is some functionality within some victim software or victim system that will do a crypto for you. And maybe you're allowed to give the plain text and have it try to encrypt it, and maybe it'll give you the ciphertext back, or maybe it'll just, you know, complain if something went wrong internally or have some other side effect. Or it could be the other way around. Maybe there's a thing within the victim system that you can give it some ciphertext and it will try and decrypt it for you, and it may give you the plain text back, or it may just error out if there was some internal error. And as a consumer of that oracle, or a caller to that oracle, you can give it, let's say, interesting inputs to try to tease some answers out of it. So it's kind of like, in some sense, like the oracle from the Matrix, right, where you can ask it questions and it gives you answers. And anyway, that's what an oracle is. It's just some part of the system that's going to do a crypto for you. And then in some cases, by giving it crafted inputs, you can... The most extreme example would be you could leak key material out of a really bad oracle, right? But in many cases, it's not going to be a full leak of the key material, but you may, as a analyst or as an exploiter, still be able to get some information leak out of it. So what are we doing today? I think we left ourselves with like I know it says simple, but I'm still a bit intimidated by this challenge. I think we've given ourselves a hard one to get started with. We're doing Byte-at-a-time ECB decryption simple. So we need to copy our oracle, or we might just create a new one. We need to create an oracle that encrypts buffers using ECB with a consistent but unknown key. So the oracle has to generate a random key and then keep using it for as many times as we want to call that oracle. The oracle should take some plain text, your string they're calling it in this case, and then append to it this after base 64 decoding it. And we are told, do not decode this string now. I suspect getting the plain text copy of whatever's inside this base 64 WAD is our goal here. So we need to write a function that uses AES-128 ECB with a consistent but unknown to us key, takes a string, slams this on the back end of it after base 64 decoding it, and then we need to make repeated calls to the oracle to leak that suffix that it's adding onto our string. Cool. We might come back and read this in a moment. For now, I'm going to copy paste all this and we will build our oracle. So what are we on? Set to challenge 12, byte-at-a-time ECB decryption. Set to challenge 12, byte-at-a-time, can't type, ECB. Do our boilerplate. Chuck in our challenge text. Cool, we've got our skeleton. So now I want to create, as we did last time, a class. And it is an AES-128 ECB append and decrypt oracle. No, append and... Is it decrypting? No, encrypting. Append and encrypt oracle. What a name. So it'll have an initializer, and it needs to generate its own key. So the key is bytes. Pull in our secrets, token bytes, that's right. Token bytes will give us random bytes. So when someone creates one of these oracles, it should generate its own key at instantiation time. Token bytes and 16 because we're lazy and we're hard coding numbers. That's all right. 16 being 128 bits, so it's the ECB. It's the AES-128 width. In main, we will do oracle equals AES-128 blah blah blah. Cool. Now, as an aside, with this like class structure, we can always do things like print oracle.key. So the consumer of this oracle is more than welcome to reach in and steal the key, but we won't be doing that. That defeats the purpose of the challenge. Now this oracle, it needs to append stuff, right? So the initializer should also take appendage, which is a bytes, and we should appendage is bytes self.appendage equals appendage. So that way when you instantiate the oracle, you need to give it this, and after that it holds onto it for you. So we should grab that. Challenge flag. Let's call it a flag. Flag is going to be base64.decode. Let's just splat. Gross. Yeah, I hate it. Should we? Nah, it's fine. Long lines never killed anyone. So the flag, we're going to then base64 decode it. No, we're not going to decode it because it needs to be bytes. And the oracle gets given an appendage of flag. Cool. So our oracle now knows what that extra little bit to tack on the end is going to be. So now our oracle encrypts buffers using ECB, consistent but unknown key. Good. Hang on, append to the... Append. If I've been saying prepend, that was my bad. Append, it goes at the end. Yeah, the unknown string goes after the input. Append before encrypting. Yep, good. So this oracle is going to have a function which is encrypt. It's going to take a prefix, which is bytes. Now, We need to pull in our ECB encryptor. AES-128 ECB encrypt, which we wrote previously. And it takes a plain text and a key, both of them bytes, and it does the padding for us. Cool. So encrypt simply returns the encryptor over, with the plain text is going to be prefix plus self.appendage, and the key is going to be self.key. That's our oracle done, right? Because now in main we can print oracle.encrypt, and a prefix we can give like empty string or empty bytes, which means that essentially the oracle is just going to be encrypting our secret appendage or our flag. Or we can do oracle.encrypt of A. They sound reasonable to me. Okay. So here's what the AES-128 EBC encryption of just the appendage looks like. And here it is with an A on the front of it. You can see they are wildly different, because AES very much changes with even slightly different inputs. On the byte level at least, of course, ECB has the Tux Penguin problem that I'm sure we'll be taking advantage of. Now it's important to note, if we created a new oracle with the appendage being the flag, then if we did these again, we're going to get different stuff the second time around. Almost certainly will. Yep, so this is different to this, and this is different to this. And the reason for that is the oracle, each oracle that you create, it's like this oracle here and this one here, they generate their own keys. So each time you create a new oracle, you get a fresh key. But if you reuse the same oracle, like if we just duplicated this line here and ran it, these two are the same, because it's the same prefix, empty bytes, and the same key, because it's the same oracle. Now we need to figure out how to get this oracle to tell us what the appendage is, which is the flag. I don't love the word appendage. Is there a better word than appendage? Postfix. Yeah, if this is a prefix, this is a postfix, isn't it? Sounds like a more mature word. Postfix. And we'll refactor that as well. The refactoring is yelling at me. That looks fine. Good. Okay. The appendage is now a postfix. So we've got our oracle. Suffix. Prefix, suffix. Thank you, Frenchie. I knew we kept you around for a reason. Suffix. I like that even better. Beautiful. So now one thing we can do is, let's take, for example, let's just start off with our empty string. Let's call that CT for ciphertext. We can print CT, but we can also print, and we have this thing called chunkify. Util import chunkify. Chunkify of CT with a chunk size of 16. Of course, because I was clever, I made it a generator, which is now hurting. That's alright. We'll just realize it. So this is, you can see, splitting it up here. Chunk, chunk, chunk. What we can do is we can also, instead of listing it, we can do chunk for chunk in. Same thing. We'll do chunk.hex. Make it a bit more readable. I'm getting hurt by the generators again, even after extolling their virtues. They're not being nice to me. Okay, so now we've got hex chunk, hex chunk, hex chunk, hex chunk. Good. Let's just yank. Let's get rid of that line. I don't like that one. Let's yank these. Instead of B, we'll do A times 16. So remember, our oracle is putting our A's at the front of the train, and then the suffix comes after. And you'll see here that this is the same as this, this is the same as this, and this is the same as this. This here is an AES encrypted chunk of all A's. And because it's chunk aligned or block aligned, it slots in nicely and just shuffles everything else along one. That's kind of cool. And we're probably going to make use of that type of thing. Instead of 16 A's, we could do 32 A's. And you see here that this is the same as this because it's two full blocks of A, and then this is the same as this. This is the same as this. So at this point, we can do things like ask the oracle to give us a block of all A's, or a block of all B's, or a block of all C's. We can say to the oracle, hey, under your current random key, what do all A's look like? What do all B's look like? What does foobar fizzbuzz 16 bytes of chosen plain text look like once you encrypt it for us? So that could be useful. Like, I suspect we're going to use a kind of trick where we let's assume the flag is something. Let's assume the flag is I'm just going to go temp equals open. Let's pull up our Alice as bytes and read it and just read the whole thing, and then just go give us the first 40 characters, and we'll print temp. We have to read it as bytes. RB. Go away. Alice was beginning to get very tired of. What we can do is we can set a temp, print the chunkify of temp with the chunk size of 16, and chop this up into 16 byte blocks. I wonder how many times I'm going to do that. Alice was beginning to get very tired of. So now we should probably pad this. Yeah, let's pad it. So temp equals, let's pull in our padder. Yep, good, we've got our padder. Pad it. Good. Pad needs a block size, which again is 16. It's gotten to the point where we really should have a cheeky constant. Block size equals 16. Block size, block size, block size, block size. Yeah, I probably should have even used it in the class, shouldn't I? Block size. Yeah, good. So let's chunkify the... so we're padding to the block size, then we're printing it, then we're chunking it and printing it. Okay, so Alice is beginning to get very tired of, and then a bunch of 8s. 8 8s to be exact. When we chunk it, we get Alice was beginning to get very tired of, and then our 8s. Now, padding may have been a mistake. Padding was a mistake. So we'll print it and we'll chunkify it, and then we'll do temp equals A plus temp. So we'll prefix it with a single A. And then we'll do this again. I suspect we're going to need to keep doing this, right? Prefixing it. Yep, no, not enough. Keep going. Not enough. I'm trying to just push this F into the next block is what I'm trying to do here. Too many. Right, there we go. So we've got enough A's to basically push that F off to the beginning of a new block. What if we then pad it? Pad temp to block size and print it again. Yeah, so this block here, because we were kind of adding A's slowly until we saw the ciphertext increase by a block. Once we know we've gotten to the point that we've kind of shoved just one character, one byte off the cliff into a new block, we know we're going to get OF, or 15 15s. So we know that this last block is the last byte of our fake flag, which Alice was beginning to get very tired of. The first byte is the last byte of our fake flag, and the rest are all F. We could then create a block, which is, new block is A plus hex OF times 15. We could throw this block at the oracle and see what popped out as the first block of our ciphertext. And if it didn't look like the last block of the ciphertext this one came out as, we would know that the last character of the flag, which is the first character of this block, is not A. And we can repeat for all the characters until it pops out. And we can then brute force one character at a time. Because then we just shove everything off one extra byte. We would know that these is going to be 14 14s. Then it's going to be whatever character we just brute forced prefixed by a new character from the flag that was just pushed over the cliff. So I think that's where we're probably going with it. But before we dive too far down that rabbit hole, we should probably check to see what the challenge suggests we do. So it turns out you can decrypt the suffix with repeated calls to the oracle. Okay, so feed 1A, 2A's, 3A's, discover the block size of the cipher. We already know it, we already know it's AES-128, but they're telling us we should basically discover that from first principles in a sense, so that way our code is going to work for AES-128, AES-256, AES-192. It'll just work for all of them, in theory. So now we need to detect that the function using ECB. You already know it, but do it anyways. Okay, cool. So now you know the block size, and you know it's ECB. Craft an input block that is exactly 1 byte short. Craft an input block that's 1 byte short. Think about what the oracle function is going to put in that last byte position. Ah, okay. Same thing I was thinking of, but the other way around. Right? Yeah, okay, I see what it wants us to do. I wonder if my way would have worked anyway. So if we make this 15 A's, sorry, we make it 16 A's, just as an example. You can see we got a full block of... A was a bad choice. I'm going to make this Z. We got a full block of Zs. And then we get Alice is beginning to get very tired of. If we make this 15 Zs, we can see that the first byte of the plain text has leaked into that first block. And we can repeat until there's no Zs there, and we will be able to have basically divide and conquer, brute forced the first block. How's it going to help us with the subsequent blocks though? That's what I don't get. So yeah, have one byte of the plain text, the suffix, fall in at the end of this block here, and then basically make a dictionary of every possible last byte by telling the oracle, give me all A's, give me A's and a B, A's and a C. Match the output of the 1 byte short input to one of the entries in your dictionary. That makes sense. You've discovered the first byte of unknown string. Repeat for the next byte. This is the first challenge we've given you whose solution will break real crypto. Lots of people know that when you encrypt something, you can see the penguin. But not everyone knows you can decrypt the contents of those ciphertexts. If our experience is any guideline, this attack will get you code execution in security tests about once a year. Bold claim, but I dig it. Now, sure, ECB, if you're like a passive observer on the wire, you can see the penguins. You can decrypt the contents of those ciphertexts. I'd probably put an asterisk here. I think there should be an asterisk saying you can decrypt the contents of those ciphertexts if the system gives you an oracle. Without an oracle, if you're just a network observer on the side, I don't know that ECB does anything more than let you see the penguins. But if you've got the oracle, obviously it's deadly. Now what I don't get is, I see how this trick's going to work for the first block of the plain text. I don't know how it's going to work for subsequent blocks. Whereas with my trick of pushing stuff off the edge, I think you can just keep going with that. What are they expecting us to do for subsequent blocks? Aha, no. Sort of, maybe. Because once you've basically brute forced that first block, Alice's begin. So what does 15 Zs look like? 15 Zs looks like this. Yeah, so Alice was begin. So then if you send 15 Zs, you can have an I fall into the second block, and this, and you can do the same trick. And then if you send 14 Zs, so you've got to work your way up and work your way back down. If you send 14, you just found out the I, you already know this, and you can have an N leak into it. So you got to go up, then you got to go down. I think I like mine better. I think mine feels easier to implement. Maybe. Maybe not. Maybe. I'm gonna try for mine. It just makes more sense to me. Okay, so the first thing they want us to do is discover the block length. Right? Was it the block size? Yeah, they want us to find the block size. Then they want us to detect that it's ECB. So let's do that. So we need a new function. Leak suffix from appending ECB oracle. And it's going to take what's it going to take? It's going to take the oracle, which is a callable, which takes bytes and gives bytes. This function here returns bytes. Pull that name in and pass. So main is going to create the oracle, and then it's going to call leak suffix from appending ECB oracle over the oracle. I'm just going to basically comment this stuff out in case we need it later. So I've got a function that's going to do the breaking. Step 1, discover block size of oracle. Step 2, prove it's ECB. Bail if it's not, because this function just won't work if it's not an ECB oracle. Discover the block size. So the base length of the ciphertext is going to be the oracle over nothing, which is basically asking the oracle to just encrypt the suffix. And then while, let's do for I in itertools, nope. So itertools.count will basically start counting from 1 and will never ever stop. It infinite loops. So basically forever, we want to, new length is the oracle over, let's do Z's for padding, Z times I. So basically just ask the oracle to, do we need, no, we don't need to be counting, do we need to be counting I? Yeah, we kind of do. Yeah, we do. Okay. So ask the oracle to encrypt a little bit more at a time, and as soon as the length of, as soon as this new length changes from the base length, we will know that a whole extra block has been put on the end. However long that block is, that is our block size. So if new length is not equal to base length, block size equals the new length minus the base length, and then break out of this loop and print the block size. And of course, PyCharm's going to yell at us because it thinks that block size might not be set to anything, but oh, hang on. I've got to run length over these, don't I? Whoops. That solves that error. PyCharm's thinking that block size could possibly be unset at this point. How do we tell PyCharm, shut up, we know what we're doing? It's going to be set. It's just the static analysis engine of PyCharm not realizing that it can't get to this point without block size being set, unless I've got a bug somewhere. We can make it shut up with this. Block size equals none. That way it can't be undefined. Satisfy the linter. Okay, so this oracle, why is it yellow? Why is it yelling at me? Because the callable is not the oracle, it's oracle.encrypt. Yeah, so we've got to pass the attacking function the encrypt method of that object. That makes sense. I'm not getting anything yelling at me, so let's run this. And we find out that the block length of this oracle is 16. Beautiful. So now if we basically write the rest of this function not with regards to the number 16 and not with regards to this block size constant here, if we always use this block size, then if we're careful, we might write a function that works for all ECB mode block ciphers of any block length. That's the dream anyway. So now we need to prove it's ECB, and if it's not, we need to bail. So we know that the oracle basically prefixes the plain text with what we send it. So ciphertext equals the oracle over Z times block size times 2. So that way we know that there's two full blocks of Z in our plain text going to the oracle. And if we just do a cheeky print chunkify over the ciphertext with the chunk size of block size and list this out, then yeah, the first two blocks are the same because it's ECB. And if it wasn't ECB, we would expect these to be different in all cases. If some of the block cipher mode returns stuff like that, but it's not ECB, it's just as bad as ECB, and we didn't learn our lessons. So if CT0 is not equal to CT1, here's where we can raise our value error. Oracle is not operating in ECB mode, or it's prepending junk. Yeah. Menstrual, what up, dude? It is good to have you here. Welcome. We are working on leaking stuff out of an ECB oracle byte at a time. Luke, been forever. Really good to have you here, dude. Welcome. Good catch with the ore, yeah. Well, you saw me thinking, because if it's prepending, if it's prepending two blocks of the same, if it's prepending two identical blocks as its junk, we're not going to catch that. But I mean, our proof of concept does not do such a dastardly thing, so we're gonna miss some cases of tomfoolery, but that's all right. At least it works on my machine, right? Okay, so we've discovered the block size of the oracle. We've proven it's ECB. Now, I didn't love this attack method. It didn't seem as straightforward as what I had in mind. So I think I will forge ahead with my crazy idea, and we can regret it later, and then we can implement what they wanted us to. But it wouldn't be fun if we didn't go off the beaten path and do something stupid, hey? So, now what do I want to do? I think I want to discover the length of the suffix, which I should be able to do by adding a byte until we spill over into a new block and then doing math. In fact, I could probably do it in here. Within here, I probably could have, based on I, figured out the length of the suffix. How do we do that? Because we know we've got I, Zs, And we also now know the block size. Suffix length equals the new len minus the block size plus 1. We need to chop off that last block. No, because PKCS7 will always add a full block of padding as soon as it becomes necessary to. If the input to PKCS7 padding is a multiple of block size, it'll always add a full block of F, so we don't need to add one. All we need to do is strip off that block, that full block of all that's at the very end. And we also need to strip off I, which is the length of our padding. That sounds right to me. Let's write a test. So there's my oracle. And the flag will be A times 8. 8 A's. How can we actually test this? We'd probably have to lift it out into its own function. Which we can do. We can do that. Leak block size and plain text and oops. Come back. Suffix len from pending oracle. Leak block size and suffix length from a pending oracle. That's fine. It doesn't even need to be ECB. Oracle is a callable which takes bytes and gives bytes, and we return a tuple of int. Yoink. Splat. Don't need the break anymore. We just return the block size and the suffix length. Don't need that either. Linter can't complain anymore. Down here, block size and suffix length equals, what did I call it? Leak. Block size and suffix length, yep. Give it the oracle. And we're good. Now we can test it. So the oracle is going to be yoink, splat. Suffix is going to be A times 8. Suffix is the suffix. So now if we leak the block size and suffix length over that oracle, we expect to get back 16 for the block size and 8 for the suffix length. Run our tests. The oracle's not callable. We need to give it oracle.encrypt. Why am I getting yelled at here? Probably just I'm reusing that label. Should still work. Tests are clean. Let's do another one where the suffix is more than a block. So we'll go times 16 plus 8. You know what? We should do the math so we can actually use it below. 24 A's should give us 16 for the block size, 24 for the suffix length. Beautiful. We now know how long the suffix is, which we can use to do math and offsets and other cool stuff. we're getting underway, but I'm going to take a quick 5-minute breather. Suggest you will do the same. Grab some water, stay hydrated, stretch your legs, and when we get back, we'll think about what we are going to do with this mess. Cool. See you on the other side of a quick short break. Alrighty, we are back. And I was thinking, instead of resting my brain, I was doing the opposite. I think we've got a way of being extra careful about this prepending junk edge case. This is like the simple case. It's a pretty happy path. But what if we do CT is the oracle over nothing? If CT0 equals CT1, maybe the oracle is prepending 2 blocks of identical junk. Because can't spell. This is going to catch the case where the junk being prepended is anything but 2 identical blocks. Pretty sure. No. If it's just prepending a single Z, or 2 Zs, or 3 Zs, less than a full block of Zs, this won't detect that. So, let's generate a chunk being token bytes of block size. That way, yeah, we're probably going to avoid that collision case. So the ciphertext is going to be the chunk times 2, or oracle over the chunk times 2. This is still going to be fine. But now, if we also see that oracle over nothing, if the first 2 are still the same, we might have that edge case where the prepended junk is 2 blocks of identical noise. Now, if CT0 equals CT1, so if that holds, what if we do, well, this is CT1 and this is CT2. So if the first 2 blocks of CT1 are not identical, it's game over straight away. But if CT2, if the first 2 blocks of CT2 over empty string are the same, if the first 2 are the same and the next 2 are not the same, no. I think I'm overcomplicating this. I had an idea and it's escaped me. You know what? Let's not bother. It's not going to be the case for our oracle anyway. To do this fails to detect the case where the oracle prepends junk, which starts with 2 identical blocks of plain text. So at least we're admitting to our gap in the comments. That'll do for now. I'm going to turn that back into CT. So we know the length of the suffix, we know the block size. At this point, what we want to do is basically push the last byte of that suffix over into the first byte of a new block. I think what we want to do, we want something called an aligning chunk. And that's going to be Z times is it the block size mod this? Is it the block size minus the suffix len mod the block size? Is there like a mathematical operator for that, by the way? Like the inverse mod, in a sense. So now, if that's correct, if that is pushing us out to precisely one new block, which is going to be all padding under correct PKCS7, then we should be able to assert that the length of the oracle over aligning chunk through -1. So one less byte than we think we need for aligning chunk equals, no, that plus the block size has to be equal to the length of the oracle over the aligning chunk, which is basically saying that we, you know, needed not 1 byte less of this aligning chunk to make it push us over into a whole new block, or give us a new block. Aligning chunk length is wrong. Now we don't actually have a doc. We're not exercising this code at all yet. So we're currently returning none. So if we leak, no, if we grab an oracle, oh come on, yoink, splat. Now if we leak the suffix over that oracle, we expect to get none back, and we just don't want this assertion to fire. And it's fired, hasn't it? Suffix is not defined. Oh, that's right. Let's start with a suffix of hello world. Run that again. And I've stuffed that up again. Oracle.encrypt. Nope, can't type. There it is. Ah, this one's fired. How have I stuffed this up? This used to be, chunk used to be Z times 16. Did I never actually exercise this code? Was it wrong all along? Okay, yeah, I don't think I ever actually ran this code. Turns out it was wrong all along. So we get a chunk of noise, and then ask the oracle to encrypt it twice, and we want the first two to be the same, but apparently they're not. Let's chunkify the ciphertext to block size. You know what, let's stop using doc tests for this for now. Let's comment that out. Nope, let's leave it there, but let's go back to using main. New flag, easier flag to start with. Hello world. Set up the oracle, run the leaker over it. Good. Run main. Chunkify doesn't have a chunk size. Bracket in the wrong spot. I'm always going to forget to actually list that out. Mistakes were made. They're the same. They look the same to me. What's going on here? Oh, I never actually chunked it, did I? I was comparing the first two bytes of ciphertext, not the first two blocks. Whoops. Let's just do a cheeky chunkify over this. So chunkify that to the block size. And then realize it as a list. Okay, the angry yellow is gone. Run this. Okay. Phew. Okay, so that's no longer firing, and this also isn't firing. Whereas if our aligning chunk was one less, then this would fire. If it was one more than it needed to be, then this would fire. So we were spot on with our aligning chunk. So our aligning chunk is enough Zs to basically cause one new block to spill over. Which is, it's probably this value I here. That's probably what it was. Yeah, it would have been. Anyway, we've recalculated it with nasty mod subtraction stuff. Okay, good. So now we can do stuff like this. Ciphertext equals the oracle over the aligning chunk over the aligning chunk. And then we print the list of chunkify CT16. This is just, we're talking hello world now. Okay. So this last block here is basically all 0f. This is just a full block of padding, which we could also write another assertion for. We could throw a prefix of what this padding would look like and check that they match, but I don't know that we need to do that. So now, if we do an aligning chunk plus another character, so we knew that that was a full block of padding. This is now 1 byte of our suffix, which is hello world, which is the exclamation mark. The exclamation mark's leaked into the plain text, and the rest is all hex 15. Like E, hex E. And we should be able to brute force that. But how do we want to structure this brute force? Let's just take some notes. So this here is hello world. It's going to look like alignment, hello world, and then it's going to be padding block. Whereas this here is going to have an extra Z in it. I don't know that this actually adds up, but anyway. And that exclamation mark leaks into here. So let's go chunks is chunkify, the list of the chunkify over the ciphertext. I shouldn't be using 16 here, should I? I should be using block size. Yes. Much better. And here we're just printing the chunks. So we could do for B in range 256, so everything up to and including 255. Ciphertext is the oracle over the bytes of B plus hex, what did I say, hex OE times 15. So, for each of the possible bytes that this bang here could have been, we'll ask the oracle to encrypt it for us. And this here is exactly one block. We've got the guess plus trailing padding. If a list of chunkify over that ciphertext to the block size, if the first block equals the last block of chunks, print B. This should find us our exclamation mark. Let's just test the theory. No. Really? Alright. Didn't work. The volts, 1999. 15 is block size minus 1. Yeah, that is true. We should do that. I don't think it's causing the problem in this case, though. This here really should be as well. You know what? Good point. Good point. Let's rewrite this. I don't think it's what's causing us our problem, but good point. So we've got B, and then we've got block size minus 1 times block size minus 1. Is Python going to accept that? Let's go PT equals that. I'm going to print PT and then do this. So let's build the plain text, print it, and then encrypt it. Yeah, so 0 and then a whole bunch of Fs. Is that what I wanted all along? What did I see in here? Nothing. Where is bang? Oh no, there we go. Okay, no. I had a That's right, because a full block of padding isn't a whole bunch of Fs, it's a whole bunch of hex 10. Yeah, that was just a mental off by one from me. Thank you, the Volt 1999. Your call that I should really be working with the block size instead meant that I was no longer making that mental stuff up, so good call. Alright, we've just brute forced out the bang. I'm just struggling to think in my head how this is actually going to be structured, because it's going to be like a loop within a loop, and we're going to have to eventually change our strategy, but we'll get there. We'll get there. So I don't need to print PT anymore. Instead of B, we'll print the chur of B. Yeah, and there's our bang. Very nice. So, first thing we probably do is for underscore in the range of the suffix. We've got the suffix length, cool. So that way we've got to repeat. We've somehow got to build the complete suffix, and let's do suffix is a list. It's going to be a list of int. Pull that name in. Instead of printing the character B, we'll do suffix dot. We want to prepend in which case this should be a dec. Where does dec live? From collections, import dec. Yeah, good. So what a dec is a double-ended list. Because in Python, when you prepend to a list, it's a very, very expensive operation. Prepending to a list is basically, Python needs to create a whole new list and put the thing that needs to be at the start, and then kind of copy paste everything over to the end of the list. Whereas a dec is a list that has cheap insertions at the start and the end. So the suffix we can prepend. No, what do we do? Append left B. Because we're going to be building it from the start. We're going to push everything along, so wouldn't make much of a difference for this function, but in general, if you ever find yourself prepending to a list, you should reach for a dec instead. So how are we actually going to iterate through all the characters in the suffix? Hello world, that's just one block, isn't it? Yeah, maybe? Maybe it's not. HE 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13. Yeah, it's just one block. Why am I getting two blocks here? What is that? Oh, because I got the that's right, the aligning chunk on the start. Cool, that's fine. We don't need this anymore. We might want it later, but we don't need it for now. Oh no, we did need it. I'm gonna grab you and put you there. You belong there. Let's go range of 1 through suffix length plus 1. Still going to give us the same number of iterations through, but now I is useful. Because instead of doing aligning chunk plus a z, we do z times I. The first time through this loop, it's going to be 1. The second time, it's going to be 2. And that's going to give us that pushing effect we're looking for. And I think that this pattern is going to break as soon as the suffix is more than a block long. We're going to have to think about how we manage that that scenario shortly. So we'll grab some ciphertext, which is the aligning chunk plus I z's. And we're going to chunkify it. Really all we need is the last chunk here. The last chunk is the list of chunkify of that for the block size. Good. Grab the last element. Pop that in there. So for each of the possible characters that could be starting that last chunk in its plain text form, what are you red for? Oh. For each of the 256, build some plain text, which is going to be no, this plain text needs to start off with the suffix we've gotten so far. No, the suffix we've gotten so far has to come after the B. Can you just do bytes over a dec? Seems like you can. So this suffix is going to start empty. So for the first time through this loop, it's going to be, the bang is going to be the winner. That'll be nothing. Yeah. That's going to be all of our OFs. Grab the ciphertext of that encrypted by the oracle. Chunkify it. Grab the first block because that's where we're doing our brute forcing work. If it matches this last chunk, we win suffix.append, left that, and break. We don't need to go through the rest of the range here. Second time through the loop. I is going to be 2. Ciphertext, we're going to have an extra Z here. It's going to push things along one more. Good. We'll grab the last chunk. Fine. For each of the bytes that the second to last character could be, build plain text. Plain text is going to be, the winning case is going to be D, because D is the second to last character of the plain text, or the flag in this synthetic case. Once we get to D, bang, padding, this should pop off. At the very end of all this, we should just be able to print bytes of suffix. And this here should be finding hello world at this point. Fingers crossed. Nope. Bytes object cannot be interpreted as an integer. Ah, no. Yes, we just needed to unpack the suffix here. We didn't need to bytes it. Good. Unpack the suffix. What are you doing there, SciView? Where do you live? Yeet. It's gone now. Try that again. We got a bang. Thank you very much. What? Okay. So I'm guessing this here never hit. So really after this loop, for B in range, if this for loop doesn't hit the break, else assert false failed. Yeah, I'd say that this here is not firing except for the bang, and it's not getting angry. There we go, failed. So we're failing to, let's go failed. Got up to bytes over suffix, bang R. Yeah, so we can see here that it got as far as the bang and got no further. It failed to brute force the D. Why did it fail on the D? Let's print PT. What does PT look like? Let's also print char I. Okay, so for character 1, it got as far as the bang and then all the Fs, and then it finished the loop. So then we had, why are these still F? They shouldn't be F anymore. How long is this string? Let's grab that. 17, something went wrong. Yeah, that shouldn't be block size -1, that should be block size minus I. Yeah, 1 will never go over 1 as second for looping. Sorry, 1 will never go over 1 as second for loop exist. So I've just swapped these ones here for I's, because they were hard-coded for the first time through the loop. Is that what you're trying to point out, or what you're pointing out in the vault? Let's run this again. Oh, there we go. Hello world. We've got it. Cool. So we've got our thanks for your help, the vault, though. I do appreciate the set of eyes, I really do. So this is working for a flag that is less than a block in length. I expect it's going to fail miserably once this gets to any sort of considerable length. Because once basically once suffix is a whole block's worth, the very next character is going to cause a whole new block to be put at the very end. And all of this -1 bizzo is just going to fail horribly. We're going to be basically, in a sense, re-brute forcing what we've already brute forced. Except it won't work. So we're going to have to probably at some point revert to or switch to a different strategy. Let's have a play. Wolf, today you learned you can else a for loop. Yeah, you can. Let me hook you up. There's a video that's getting a little bit aged now, but it's brilliant. Oh, I finally couldn't remember what it's called. Is it Raymond? Python. Beautiful. Transforming code into beautiful idiomatic Python. It's 9 years old. There's a comment on this video that I think describes what's changed in the meantime, but the concepts, like the core concepts of it, are great. And I'll drop that link in chat now. Wolf, watch that video. I think you'll love it. I'm pretty sure it's what taught me things like deck being the right structure for a double-ended list. It's what taught me about elsing a for loop, which is basically to say if this for loop completes and it doesn't break, this runs, and it's beautiful. What else in there was really good? It taught me about named tuples. I don't know if it taught me about data classes. I think I got that from another one of his videos. Raymond he's a gem. Wolf, you'll love that video. And everyone else as well. You'll love that video. Check it out and you'll learn a bunch of stuff that you'll be like, I never knew Python could do that. I've been doing things the silly way forever. And you'll just have a whole bunch of stuff you can go through all your code and make it much more tidy. I can't recommend it enough.
Time is fleeting, you say. When I grab your hand, you turn away.
Let's have a play. Let's comment this out for now. And then bring back our hello world. No, it needs to be longer. What happened to Alice? Where's Alice? Where do we put Alice? Here. Let's bring all this code back. I miss this code. Let's switch to... Actually, you know what? You know what could be fun? Let's learn the last block of our challenge flag. Just to whet the appetites. Just drove by. Fascinating. And then, of course, as expected, it kind of blows up once it gets to that last block, or tries going beyond that last block. Frenchie's out. Dude, so good to have you here. Look after yourself, and I will catch you on the flip side. Sweet dreams, my friend. Let's stop doing that. But let's keep the flag being this mess. No, let's not. Let's have the flag be hello world times 2. I don't want that, I don't want that, I don't want that, I don't want temp, I don't want temp. So I'm going to print the flag chunkified. Let's just print the flag chunkified. Why are you angry? Ah, look at the return there. Let's run main. So hello world, HE, low world. For I in range of 16. let's flag 2 equals z times I. Let's make 16 plus 1. Z times I plus the flag. The vault block size. I'm just having a play around here. I'm just trying to get a visual concept of how things change as you pad them and new blocks get born. So this is not production code. I'm just having a play. I don't want that anymore. Flag 2 is that. Flag 2 equals, do we have to pad it? Yeah, we have to pad it. Let's pad it to, again, so this should be the block size. This here, this number here is coincidentally the block size. It's just a number I picked. Chunks is the chunkify over flag 2 to the block size. Print chunks. No, print I and then chunks. Thanks, I hate it. Okay. pprint has screwed me before, but let's pull it in for fun. From pprint, import pprint. Let's pretty print this. Yeah, now it's screwing me because it's trying to wrap lines. Can pprint like not wrap lines? Do we just give it width equals 0? Width must not be 0. Alright, you get a bunch of 9s. That's no better than what I... Damn it. Okay. Let's print I and then print for chunk in chunks. Print the chunk. Oh, it's no better, is it? Print the chunks. Print the list of the chunks. I don't love it, but it'll have to do. 4, 3, 2, 1. And then we get a whole new block born. You know what? Let's take this out to 32 plus 1. No. Let's take it. No, let's do 32 plus 1. That's fine. Okay, so this is where a new block gets born. And here's where our brute forcing starts. I'm gonna change my flag because that space is gonna throw me off. Okay. Here's where a new block gets born. Here's where our brute force starts with a bang. D-bang, LD bang, we can get to hello, we can get to low world, LO world, hello world. This is where our previous brute force was able to finish because it didn't have another hello world to work through. So now new code, in fact, if we quickly run, that's fine, we can keep that. If we quickly run this, how far through hello world did it get? It got up to debang hello world. Debang hello world. So if we get rid of that, run this. So I was able to brute force debang hello world. Then as soon as it tried to get the L, that's what caused this new block to be born. And it was brute forcing this as though it was this block. Oh, but we're gonna... That's fine. We can do that. We can account for that here. Once I gets to a multiple of I gets to a multiple of the block size, this -1 has to change. We basically need to go back a block. But then the very next, like that case I can handle. In fact, let's work on getting LD bang hello world. I think we can do that. That shouldn't be too bad. So let's bring this back in, run it, and we got D bang hello world. We want that. We want to get to LD. And it's to do with this here. That really should be -1 minus I divided by block size. // is like a divide and floor in Python. So like 3/2 is normally 1.5. 3//2, it floors it to 1. And it always rounds down, because 1.5 would normally round up, but // always floors, always goes down. So this here, I// block size. Because once we start working on this, we might have an off by 1 here still. How long is debang hello world? Oh, we might be fine. 15. No, we're good, because then this is about to. So for LD, I is going to be 16. Previously, on the previous round, 15 / the block size, which happens to be 16, is 0, but 16 / block size becomes 1. So then we start looking back at the second to last block. So this now should find LD bang hello world. We've got the D bang. What just happened? Did that just like almost work? Oh no, this is our playground from down the bottom. Okay, that I didn't think that was going to work, but it did. But we're being a bit wasteful. We're being wasteful in as much as I thought I'd have to basically trim this PT to be the first block only. Because you can see after the LD bang hello world, you get RLD bang hello world and the bang falls off. I thought we'd have to be trimming that, but it's fine because when you that is part of PT and you throw it at the oracle, it just naturally falls into the next block anyway. It means we are sending more bytes to the oracle than we would otherwise need to. We may as well trim PT to just be the first n bytes of it where n is the block length. So we may as well. This list here, before we bytes it, we can just go up to the block size. It just makes it a bit cheaper in case, we're sending stuff over the wire and the suffix is like a gigabyte. That savings will add up over time. This code is looking awful. I'm so sorry, by the way. @Wolf Jello World. I know it's past dinner time for me. I'm going to have to peel off shortly. I had a snack before I started, but it's not enough. But I don't think I'll be eating Jello World for dinner. So this should give us some savings on consumption of the oracle. It should still work. What have we got? Hello world, hello world. I mean, I'm happy with that. Instead of printing the bytes as suffix, we just return it, right? And we're done. Are we done? Instead of running it over hello world times 2, we run it over the challenge flag and we print Oh, we've got some noise here, actually. Oh, no. Where are we? Rolling on my 5 with the rack top down so my hair can blow. I think we're good. We've just got some debug noise coming from places that we can clean up. Don't need that, don't need that. Don't need hello world times 2. That looks fine. These comments are getting yeeted. What if we just look for print? Let's tidy up our imports. Don't need that. Don't need that. Let's do res equals that and then print res.decode because it looks like it's literature. It looks like it's text. We good? That there, theoretically, is this here. So let's add that to the test. Whoops. Leak suffix. Yeah, it's a bad test. We'll get rid of that one. Of course, I just cleared my clipboard. Yank 5 down. Plonk. So the flag is that. Decode it. Create our oracle, which does oracle things. We'll do a recap of that in a moment. And then we leak the suffix from the appending oracle by giving it the oracle. And then res should equal flag. Right? If that gives us a true, we are done. I'm happy with that. Test pass. And that is how you leverage a appending ECB mode oracle. Pretty sure it doesn't. Let's deep breaths. Okay, so what have we done? We have completed Byte-at-a-time ECB decryption. So we have this oracle. And this oracle, once you instantiate it, it generates its own random key and stashes it in its own properties. And when you instantiate it, it takes a suffix as well, which is actually our flag. Our goal is to discover what the suffix of an oracle is. And the oracle gives us an API. The API takes a prefix, so we control what goes on front. And what it does is it takes what we give it, slams on the end of it that secret message, that flag, that suffix, and then encrypts it using AES-128 ECB. Now, I'm pretty sure AES is irrelevant to this challenge. I'm pretty sure 128 is irrelevant to this challenge. I'm pretty sure this will work for any block mode cipher of any block size as long as it's operating in an ECB mode. So given this oracle, what do? First thing we do is we leak the block size and we get the suffix length. And we do that by just asking the oracle, hey, use empty string for your prefix. Basically just asking the oracle, hey, encrypt your plain text, encrypt your suffix, and give us the ciphertext. And then we basically start giving it prefixes of gradually increasing length until the ciphertext we get back from the oracle increases in size. And it's going to increase in size by the block size all in one big whack. And as soon as it does that, we can learn two things. We can learn what the block size of the cipher is, because it's how much it increased its size in that last round. But we can also learn the length of the suffix that is hidden inside the oracle. And we can learn the suffix length. It's based on things. I'm fading. 7 o'clock streams are probably a bad idea, or at least I need to eat beforehand. The suffix length we learn... No, I'm losing it. How did we work out the suffix length? Alright, we basically just take the length of the ciphertext we get back in the very end there, with that whole extra new block added. We chop off that last block, and we also chop off how many padding bytes we needed to add to get that spillover to occur, and bang, there's our length of the hidden suffix. We then make a naive attempt at proving that the oracle's operating in ECB mode, and it's super naive. We just basically chuck it two identical full blocks and ensure that what we get back has that tux penguin pattern where the first two blocks of the response or the ciphertext are the same. We then build ourselves an aligning chunk, which is basically a chunk that's big enough to cause that spillover to happen. And we always basically put the aligning chunk on the start of things. And so then we gradually send more and more padding stuff after the aligning chunk to cause bytes to slowly spill over into a new fresh padded block. And then we just basically do a dictionary attack, divide and conquer. Each time we kind of get to a new character spilling into a new fresh block, we just start throwing stuff at the oracle to say, hey, I've only got to guess 256 things to guess that new byte, and do a byte by byte attack. So I'm happy with that, and I am crashing real hard, so I'm going to pull up stumps pretty early this evening, but I've got to go get something to eat, so thank you very much for joining me. The Vault 1999, thank you for your support and your help. I greatly appreciated that bug that you caught. Atwolf and anyone else who's stuck around till the end, thanks for your patience. I'll be streaming again probably sometime in the next few days. But until then, hope you stay safe, hope you enjoy your week, and I'll catch you on the next one. Bye for now.